All right. Thank you, everyone, for coming to see my slideshow, listen to my quote unquote lecture. Um, so, yeah, we've learned a lot this semester with regards to logistics optimization problems. In particular, with column generation, we applied it to solve the vehicle routing problem to obtain a sort of lower bound to a very difficult solution. So, today, I want to introduce what's called the stabilized column generation. As a standard method sometimes has slow convergence issues, which means it takes many iterations or columns generated to reach an optimal solution. So let's dive in. So some issues with the standard column generation method is that it can display slow convergence, like we said. This can happen for a few following reasons. I'm gonna highlight two. Just a general large size of a restricted master linear program. Um, Even though the column generation procedure is very useful and beneficial, uh, it still depends on how many variables there are and takes many columns generated to reach an optimal solution sometimes. So in the case of vehicle routing problems, we have a lot of different columns in that, especially if there's like 3 vehicles and rather than 14 vehicles, then the number of columns grows and it becomes really tough to find a quick convergence to the solution. Another key reason for slow convergence is that sometimes these linear programs have degeneracy in them, and which could really slow down the process. And yeah, a lot of the literature out there, they introduced the stabilize because of this degeneracy problem. So in 1999, four mathematicians, Dumeril, Villeneuve, Desrocher, and Hansen, I don't know if I might have butchered that pronunciation, but they observe a few things about the standard column generation procedure. The first was that the dual variable values for the when you solve the master problem, they often oscillate wildly in the first few iterations, which means that the dual variable values at the optimum is very different from the very first few iterations. And with that, it also means that the columns in the optimal basis are usually generated the last few iterations when the dual variable is already close to their dual variable optimum decision variable values, if that makes sense. And so we needed a way to stabilize this column generation procedure so as to generate better columns from the get-go. All right, so let's sort of dive in. So the idea is to stabilize the objective function by penalizing dual solutions that are far from the stability center. This will make a little more sense when we dive into sort of the formulation, the numbers behind it. But the idea is to update the stability center to converge to a dual optimal solution. So by updating the stability center, it'll reach it a lot faster. We're penalizing it if it's far, and if the dual variable values are oscillating a lot from the current iteration. And we're also going to update the stabilized objective function to converge to a null solution. So this will make more sense in the next slide. So let's go. So here we have a standard, just primal linear programming formulation with the cost vector, the x decision variable vector, the constraints, and the non-negativity constraint. And just know this could be, we can make this integer and use a linear relaxation to find a lower bound for integer solution as well. So this is a dual counterpart where the pi represents the dual variables. So maybe on like the right hand side constraint values will be the pi. Or sorry, no, that will be the b, and the pi will be the dual variable values for that. So here we introduce the stabilized formulation. So we're going to denote it as p under subscript e. So this is the same. You can ignore the e, but I just wanted to denote it as the stabilized format. But these x values are the same. So we introduce these artificial variables y1 and y2. They're bounded by these predetermined epsilon 1 and epsilon 2 bounds. And also these sigma 1 and sigma 2, they're sort of a penalizing sort of scalar to these bounded variables. So the idea is that as we bring new columns into the master problem, if it's a bad column, then we're going to make it a stricter sort of a larger bound, which means, if you want to minimize, then it's going to be bounded by this or limited by these scalars. So yeah, if we look at its dual as well from this formulation, we see that the epsilons also are the scalars for these decision variables, the W1 and W2. And if you kind of look at the whole formulation, we see that the decision variable pi is bounded by the sigma, which is a scalar here. And similarly, the decision variable for the y1 and y2 is bounded by these epsilons. So the idea is to update these epsilons and sigmas with each iteration. If column that is brought in is not too close to the current dual values, then let's make it stricter. If not, let's decrease it so that it converges faster. So it's pretty difficult to find a numerical example for this problem. A lot of the papers are just applying it to large data sets, especially vehicle routing problems, instances. And so it's pretty difficult to pretty difficult to find a good numerical example that's easy to understand. But yeah, I'm gonna just try my best to explain it. So let's go back to the cutting stock problem example. So the standard given stock rolls of width W, determine how to cut these stock rolls so that BI units of width WI for these 1 through M constraints are produced and the total number of stock rolls is minimized. All right, so let's say for our example that our stock rolls, each one is a maximum of 15 feet, and then we have 3 different types. 4-foot boards, 6-foot boards, and 7-foot boards. And the 15-foot boards are cut to meet the following requirements. So there's demand of 80 of the 4-foot boards, 50 of the 6-foot boards, and 100 of the 7-foot boards. And so these 15-foot boards can be cut into various patterns. So for our example, we'll just stick with 6 specific patterns. So here, let A1, so here, let's first describe the X1s. So this is one pattern X1 where we have 3 4-foot boards, 0 6-foot boards, and 0 7-foot boards. Since it's bounded by 15, if you have 3 4-foot boards, then you have 12 feet used, and you can't make a 6-foot or 7-foot board. And same idea here, 2 of 6-foot, 2 of 7-foot, and then, yeah. All right, so our primal cutting stock formulation would be to minimize the material used, number of boards used. Here are the constraints set up. All right. And here's our demands 80, 50, and 100. So what we're going to do, or we're going to introduce the artificial variables y1 and y2 and also get the dual counterpart and try our best to sort of explain how this would work. I did have a problem. I wasn't able to find a good way to update the epsilon and sigma values, so I'm just going to show you the formulation and sort of explain how it would work. Right, so let's format it or formulate it with the stabilized formulation. So same thing as before, but we've introduced the y1 and y2 artificial variables. We see that they're a new decision variable as well. And let's see. Right. So yeah, here we've added it all in. So the y1 vector is actually composed of these 3 components, and the y2 similarly is these 3 components. So if we want to do a column generation formulation of this, let's just choose the simplest ones. So we need a subset of the decision variables. So let's stick with x1, x2, and x3 in the beginning. So we can get rid of all these. And the idea is we'll have these three in the basis and then search for potential ones that would be a better optimal solution. Okay, so the dual counterpart for this would be, oh, and also by solving the primal, we get the dual values as well for the column generation. So, but just to show you the dual formulation, it'd be something like this. And by solving that subset, it'll be similar. It'll be the same thing as doing this. Getting rid of the pattern 4, 5, and 6 constraints. And yeah, so we're going to solve this. And so by solving this, we get pi 1, pi 2, pi 3 optimal values for those three different patterns. And then we're going to save. And then we're going to save our subproblem where we get that pi 1 optimum value, pi 2 optimum value, and pi 3 optimum value. So if this was just a general, problem without these constraints, then the pi 1, pi 2, pi 3 will be different. But because we have these epsilon 1, epsilon 2, or w1, w2, and in the previous, the y1 and y2, it'll return the values of x, but also the values of y. So the optimum dual values could be different. All right, so but the idea is that we use the pi 1, pi 3 values, which are different because of the new variables that we brought in. So the idea is that if you remember the cutting stock problem, we have this maximize, and this is kind of the one where the constraint is violated. So if this is greater than 1, then that means we're not at the optimum yet with the columns in our basis. So we're going to find the maximum that's greater than 1 and bring it into our basis. And then we will continue the process that we did. So the additional step that we do, though, is that we update the epsilon and sigma values as well. So if the values that we brought in are pretty close to the dual variable, the pi values that we've had, then we'll sort of decrease the epsilon sigma values. Otherwise, we increase them because we want to make sure it stays within like a stable sort of, doesn't oscillate too wildly, if that makes sense. And I did forget to reiterate, sorry. Let me go back just real quick. So to know that we're at an optimal solution, if y1 and y2 is 0 here, then this will be the same as this, right? So if when we solve this problem, the restrict master problem here, and we get that y1 and y2 is 0, then we have our optimal solution. And we know that y1 and y2 is 0 if epsilon 2 equals 0. But also if w and w2, if they equal 0, then we'll also have an optimal solution because this maximize and this minimize will essentially be the same value. So that's when we know we have an optimal solution. And the idea is that by introducing these artificial variables and these penalizing scalars, it will help find the columns a lot faster. So let's go back real quick. All right. Sorry about going back and forth. Forgot to mention that key component. All right, so that's sort of the general idea, if that made sense. But here we have the standard column generation procedure, and this is the stabilized. You don't have to know the details that much, but this optimizer is pretty much solving that restricted master problem. And we get the x values and the optimal pi values for the restricted problem where we have a subset of the decision variables. Well, the difference here with the stabilized, we also get the y1, y2, and w1, w2 values, which could change actually the pi and x values as well. So the pi values could be different, but because it's stabilized, the idea is that the convergence will be a lot quicker. And we see that another key component step difference here is that we update the sigma and the epsilons as we go. So yeah, it's pretty tough to find a good numerical example, but I think it makes sense to show an example or just a sample set that someone did where they use a stabilized method and it saved them a lot of computational time. So this is a bus routing problem done by these three authors in one of their papers. The problem is figuring out bus routes to pick up children from various stops and bring them to school. And this BP is a branch and price without a stabilized column generation. This branch cut and price method utilizes a stabilized column generation. And if you compare the CPU or the computing times, we see that it's a lot more efficient here, as you can see with the stabilized method. And if you look at a lot of the literature out there, the stabilized is used quite a bit, just because there's a lot of degenerate solutions in the master linear programs. So to help bypass that, introducing those penalizing stabilizers helps reduce the computing time. So yeah, thank you guys for taking a listen. If you have any questions, please feel free to email me. Sorry I couldn't make it to class today. I'm in Korea at the moment. I have to wake up early in the morning tomorrow. So really hope you guys enjoy it and hope you have a great day.